we're going to start to generalize this theorem here and this strategy that took place in this last example. Oftentimes, we're concerned with counting a specific thing here. So often, we are concerned with the number of ways of partitioning a set. Number of ways of partitioning a set of n objects into R subsets called cells. N objects into R subsets called cells. And to try to digest some of this formal terminology, not a bad way to think of a cell is like think of like just actual cells, like maybe like a prison cell or like a room, right? You have N people and you want to split them up into R different cells. A partition, this word partition actually is very specific. A partition is when, let's clear that up a little bit, is when the intersection of any pair, the intersection of any pair, the intersection of any pair of subsets is empty. Of subsets is empty, the empty set, there's no intersection. And the union gives you the original set, or the whole set. Gives you the original set, okay? All right. So in a mathematical sense, for those of you who are math and or stat majors or minors here, here is this concept in formal notation. We would say S, the set S, is partitioned into different cells or sets S1, S2, yada, yada, yada. How many subsets do we have here? We have R subsets, so we'll say up to S sub R if the intersection of any two is empty. So that would mean then you pick any S sub I and intersect it with any other S sub j, and you get the empty set there. And of course, we're not intersecting a set with itself, so we'll say I is not equal to j. And the union gives you the original set. The union gives you the original set. The union of all S sub i's as I goes from 1 to R gives you the original set. All right. And again, a nice way I think of this is if you have, for example, like 10 people, 10 criminals or felons or whatever, 10 people, and you're going to put them in different jail cells, right? You can't put one person in more than one cell. That intersection's always empty. And you're spreading all of them out so that when you look at all the people, you have all the original sets, okay? And again, I think that's a good example is because it doesn't really matter who goes in the cell first, all right? The order of the elements within a cell is of no importance here. The order of the elements within a cell is of no importance. Of no importance, okay? The order of elements within a cell is of no importance. And this leads to a theorem that's going to look almost identical to the previous theorem, but is slightly more generic. Theorem 2.5 in our e-text. The number of ways of partitioning a set. The number of ways of partitioning a set of n objects into R cells, n objects into R cells with n1 elements in the first cell, n1 elements in the first cell, and 2 in the second cell, and so on and so forth, etc. The different ways of doing this is we have some notation here. This is not NPR, but it's going to have these giant parentheses. So our n is the number of total objects, and then we have n1 elements in the first cell, comma, n2 elements in the second cell, comma, and then so on and so forth, all the way to n sub r elements. And what does this symbol mean? This is actually that very similar looking factorial fraction. It's n factorial over n1 factorial times n2 factorial times n3 factorial, yada, 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 times n sub r factorial. Now, what we have here, though, is the sum of the actual numbers that you're putting in the cells. If it's a partition, you have to get the original set. So n1 plus n2 plus n3 plus nr, this has to add up to n. That has to add up to n. Let's put an example to this to try to help clarify. In how many ways can 7 graduate students be assigned how do you spell assigned here, Aaron? Let's try that again. Let me get rid of that. Can be assigned to 1 triple bed and 2 double bed hotel rooms during a conference. Well, 1 triple bed and 2 double bed hotel rooms. So in one room, the 1 triple bed means there's 3 beds, and then there's 2 rooms that are there's 2 double bed hotel rooms. So there's 2 rooms that have 2 beds. So 1 triple, 1 holds 3, 1 has 3 beds, and there's 2 other rooms that have 2 beds. So you're taking your 7 students and you're partitioning them, right? The order does not matter here, right? If you put person A, B, and C in the triple, it doesn't matter if A is in there first. That's the same thing as putting persons B, A, and C in the triple. So there are 7, total of 7 objects. You're going to group 3 of them together in one room. You're grouping another 2 together in another room and another 2 in the last room. 7 factorial over 3 factorial, 2 factorial, 2 factorial. Working on the arithmetic, run that through a calculator, we should get to 10. All right, this gives way now. We are ready to briefly discuss combinations. In many problems, many problems, we want to choose R items. We want to choose R items from N. And we don't care about the order. And we don't care about the order. We want to choose R items from N, and we don't care about the order. So essentially, what a combination is, then, we'll go ahead and define this, or our definition. A combination is really just a partition, and you have 2 cells. R of them you've chosen, that's one cell, and the other ones you did not choose. That's a different cell. a combination is a partition with two cells. Two cells. One containing the R items you've wanted to select, one containing R items, and the other cell has the remaining n minus R. Right? If there's n items, you put R in one cell, then there are n minus R left to go in the other. Okay? So we'll go ahead just to align with the theorems in the e-text. I'll mention this is theorem 2.6, but a combination using the notation above is just n items and you have two cells. R of them goes in one and n minus R goes in the other. Okay? By default, this is so common. If you only have two cells, you really only need to know the quantity that's in one cell, because by default, then, by looking at the complement count, you can figure out how many are in the other cell. And so we tend to just write this as n choose R, and we don't write the second n minus R in that bottom part. So we see this n choose R, and then again, what is this by definition by that theorem above? This would be n factorial, R factorial items in one, or R items in one cell, so that's R factorial, and then n minus R in the other cell, times n minus R factorial. That is our combination. That is a combination. So, partition into two cells. Here's a quick example. How many ways are there? How many ways are there to select a jury? To select a jury of 3 people. From a pool of 8. 3 people from a pool of 8. 3 people from a pool of 8. Notice that this is not a permutation question. This is not 8p3 because the ordering doesn't matter. You're just either in the jury or you are not. It's a partition into 2 cells. So this is simply 8 choose 3, which is 8 factorial over 3 factorial times 5 factorial. And working out the arithmetic there, we should get to 56. We should get to 56. And there is your combinations. Those are combinations. So, large sweeping broad stroke summary here for this section. And there's multiple different things and types of permutations and scenarios for permutations. But permutations, right, you're looking at the ordering matters. Order matters. The way things are selected, order matters. And in combinations, it doesn't matter who is picked first. The order does not matter. The order does not matter when you're talking about combinations, okay? Right? So, broad strokes there, if you are coming back to a question like this at a later time, right? And it's not directly below theorem 2.6, right? You have to read this question and try to identify, should I be using a combination counting technique or should I be using a permutation combination technique? And the first question I ask myself is, well, does the order matter? And if the order matters, then I might want to think permutation technique. If the order does not matter, like in here, you're just picking 3 people to a jury. It doesn't matter who gets selected first. Then I'm thinking combinations, okay? All right. That'll do it for us here in this video. As usual, please post comments, questions, and concerns in the discussion threads below.